So chapter 4 is on light and energy. So it's different electromagnetic spectrums that we have. Okay. So let's go through this here. And there's different wavelengths of light, and that's what we see. We see in the visible spectrum anywhere from 700 nanometers to 400 nanometers. Okay. And we use different measurements when we're dealing with light. We'll use wavelength, and we use frequency. Wavelength, okay, is how long a light wave is from the crest to the other crest. That's your wavelength. And wavelength is given the symbol of lambda, Greek letter lambda. That's your wavelength. Okay, your frequency is how often it passes a certain point. So as the light wave is moving, you have one point that's stationary. As that passes through, for the same point on the wave to pass through again, that's the frequency. Lambda is expressed in nanometers, nano 10 to the minus 9, and frequency is expressed in per second. So it's S to the minus 1. It's like how many cycles per second. Like your light cycle, 60 cycles per second. Okay. Now energy is dependent upon wavelength and frequency. If the wavelength is really large, it's a low energy. If the wavelength is really short, that's high energy. You can see the difference. A high energy wave has very small wavelength. Low energy wave has very long wavelength. So wavelength increases, as energy increases, wavelength decreases. Okay? And energy is related to wavelength by C. C equals wavelength times frequency. And C is the speed of light. So C is 3.00 times 10 to the 8 meters per second. That's C. That's a constant. That's your speed of light. So your wavelength times your frequency equals your speed of light. How's my voice doing with the echoing?
It's doing good, but I was going to ask, are you writing something on your screen? Because if you are, it's not showing up.
Yeah, that's what I was going to say too.
Yeah, I am writing on my screen. How come it's not showing up?
Yeah, nothing. I can't see nothing.
Boy. We're having all kinds of troubles here today, aren't we? I did check it. Okay, why are we not connected here? It shouldn't have done anything with my voice doing that. All right, stop share. Take this and go back. Keynotes. All right, share screen. And iPad. Okay, y'all see my iPad screen, right?
Yes.
Okay. Let's go to my chemistry. Let's go to. How's that?
That's good.
Yes.
All right. Boy, it's been one thing after another day. But you hear my voice now good, right?
Yes, perfectly.
Okay. So we had wavelength is going from the crest of one to the crest of the other. That's your wavelength, and that's lambda. Frequency is how often a wave passes a certain point at a particular time. That's per second. So lambda is measured in nanometers. Frequency is measured in per second. And energy is related to wavelength and to frequency because they're related to each other. But long wavelengths is low energy. Very short wavelengths is very high energy. Okay, so if the wavelength's going like that, that's your high energy. Very long wavelength is very low energy. Wavelength and frequency are related. C equals lambda. Whoa, can't write that one. C equals lambda mu. Wavelength times frequency equals the speed of light. The speed of light is 3.00 times 10 to the 8 meters per second. That's a constant. Okay? So that's our formula. The speed of light is equal to your wavelength times your frequency. So if you know wavelength, you can calculate frequency. If you know frequency, you can calculate wavelength. Okay. So one of the problems here says, when we're dealing with light, light is in photons. That's a packet of energy. That's its wavelength. It's released as a photon. That's your packet of energy of light. So let's take one of the examples from the book here. If it says a beam of green light has a wavelength of 500 nanometers, what's the frequency? Okay. So if you want to do that, let's move this on. So if you have a beam of green light has a wavelength equal to 500 nanometers, and it wants to know the frequency, nanometers. So we know C is equal to lambda nu, okay, wavelength times frequency, and you're looking for frequency. So frequency equals C divided by lambda, right? Just moving those around. Divide lambda onto both sides. Because you want to solve for frequency because that's what you want. So we know C, 3.00 times 10 to the 8 meters per second. And the frequency is, the wavelength is 500 nanometers. Okay, everybody good so far with that? Setting it up?
Yeah.
Okay, now look at, on the top is meters and the bottom is nanometers. You can't have that. So we've got to have, we got to convert nanometers to meters. Nano is the same thing as 10 to the minus 9. That's what nano means in the metric system. Okay, so now nanometers cancel, meters cancel, and we're left with per second, which is frequency. Remember, lambda is measured in length, like nanometers. Frequency is per second. Like per second is a hertz, like 60 hertz, 60 cycles per second. So to do that, we take 300, or we take 3 divided by 500. So let's get your calculator out, and you'll do 3 divided by 500 equals 0.006. So 0.006. And then you got 10 to the 8. And we bring this up, it becomes 10 to the 9th.
We can't see it anymore.
What's that?
I don't think you're writing anymore. Can anybody see that?
No.
No.
It stopped writing again.
This is having all kinds of trouble doing that today. I don't know why.
It was going good and it just stopped. Is the cord like all the way pushed in on the pad you're writing on? Maybe
Yeah,
loose. What about the wall? Like is it plugged into the wall? Is it loose on the wall?
No, there's no plug on. Let me try it again.
Oh, I can see your mouse. Try writing again. Try writing now.
No, it's still not doing it.
No, just your mouse. We can see your mouse.
All right, stop share. And let's start the share again. Okay, now you can see all that.
Yes.
Yeah.
We can see you erasing it. Yeah.
I don't know why it does that. So 0.006, and then you got 10 to the 8, and we bring this up, becomes 10 to the 9th, right? 0.006, 10 to the 8th, and bring that up 10 to the minus 9. Okay? Yeah, let's see where we were at. Okay, so 0.006 or 3 divided by 500. Okay, 10 to the 8th and 10 to the 9th is 10 to the 9th is 10 to the 17. So we're gonna make this 6. And we're good to the one significant digit here. How much we got? 3 significant digits, 500. So we got 6.00. So I moved this decimal point 1, 2, 3 places. I've made it bigger, right? I move this decimal point here. 1, 2, 3. Make that smaller by 3. So 6.00 times 10 to the 14th per second. And that's your frequency. I know it's kind of hard to interrupt with going through the stopped working. Okay, but 0.006 was our answer from doing the math right here. Then we took our exponents. We came at 10 to 17. Then I moved this decimal point 1, 2, 3 places. Okay. I made it bigger by 3. So 0.06 is smaller than 6. So I made that into 6.00. So I moved it 3 places. I made it bigger by 3. I made my exponent smaller by 3. So 17 minus 3 is 14. And you get 6.00 times 10 to the 14 per second. And that's your frequency. Okay, so if you're ever giving frequency, you can find the wavelength. If you're giving the wavelength, you can find the frequency. If we're given a frequency, yeah, that's one with the frequency. Let's say we have a frequency of blue light. Blue light has 6.41 times 10 to the 14. Okay, so blue light, you know the frequency is 6.41 times 10 to the 14th per second. Okay, that's your frequency. And you know, the speed of light is equal to your wavelength times your frequency. So now we're looking for wavelength. So wavelength is equal to C divided by frequency. Just divide frequency on both sides, just rearrange your equation. We C is 3.00 times 10 to the 8 meters per second. Frequency is 6.41 times 10 to the 14th per second. The per seconds cancel, and we're left with meters. Okay, so then we do the math. And you get 3, do your integers first. So 3 divided by 6.41 equals 0.468. Okay, we're still writing good. 0.468 meters. Okay, and then you do your 10 to the 8. Well, you know, 10 to the 8, which is on top, and we move this one up, right? We move the 10 to the 14th. We've done these both. We do save the exponents to last. 10 to the 8. We bring that up. 10 to the minus 14. Oh, it stopped writing again. This is really, I don't know what is wrong with the website here. It keeps kicking off the connection. Okay. Please know how to get it back now. Okay, it does it. All right, so you got 0.468, 10 to the 8, 10 to the minus 14. Okay, so this is 10 to the what? So 8 minus 14 is negative 6, right? 8 minus 14 is negative 6.
Yes.
Okay, so we got 0.468 times 10 to the minus 6 meters. So we're going to move this one place, right? To make it 4.68, put in scientific notation. So we'll end up with 4.68 times 10 to the, and I moved it one place, and I made that number bigger. Okay, I went from 0.4 to 4. So I can make this one smaller by 1. So 10 to the minus 7 meters. And wavelength is usually expressed in nanometers. So we can convert meters to nanometers. So we got 4.68 times 10 to the minus 7 meters. Meters on the bottom, nanometers on top. Nano is 10 to the minus 9. Okay. So we move this up. This becomes 10 to the 9th. So 9 minus 7 is 2. So we got 4.68 times 10 to the 2 nanometers, or 468 nanometers. I think it's 4.68 times 10 to the 2. And that would be your answer. That's how much, that's the wavelength of a blue light that has a frequency of 6.41 times 10 to the 14 per second. Okay, so if you're given frequency, you can determine wavelength. If you're given wavelength, you can determine frequency. Because the wavelength times the frequency is equal to the speed of light. And the speed of light's a constant. It's always going to be 3.00 times 10 to the 8 meters per second. Okay, questions with that? Hopefully my thing keeps writing here. All right. And next one is energy. The energy of a photon. Photon is just a unit of measurement of energy. So the energy of photon is equal to h mu. Okay. So energy is E. H is another constant. H is what's called Planck's constant. Planck's constant is equal to 6.626. Right, where's Planck's constant in your book here? 6.626. 6.626 times 10 to the negative 34 joule seconds. Joule is a measurement of energy, seconds measurement of time. So Planck's constant is 6.626 times 10 to the minus 34 joule seconds. That's just a constant all the time, just like speed of light. Okay? So if you want to calculate the energy of light and you're given the frequency, you just multiply by Planck's constant. Okay? If you're given the wavelength, you have to do a little bit more. So let's do one with frequency. If we're given a frequency, let's say the frequency is equal to 7.59 times 10 to the minus, say 14, 10 to the 14 per second. Okay, so you're given this frequency, like this would be like in a typical midterm question. You're given the frequency. What's the energy of the photon of that frequency? Again, photon is just a measurement and a particle of light.
Your board went out again, I think.
Oh man, this is really crazy. I don't know why it's doing this. Okay, it's back. Might be have something to do with the, I'll have to reset everything, but it's not worth it right now. 7.59 times 10 to the 14 is your frequency. Okay, so energy is equal to H, which is 6.626 times 10 to the 34 joule seconds, times 7.59 times 10 to the 14th per second. You have a per second and a second, they cancel, and you're left with joules, which is what you want. Joules is a unit of energy. So to do those calculations, you take 6.626 times 7.59. Again, save your exponents for later. So circle them so you don't forget it. And then do your exponents. Do that on a calculator or your iPhone. Okay, just do 6.626 times 7.59. Whoops, I think I did that wrong. 6.626. Anyway, 6.626 times 7.59 equals 50.29134. That's what you got on your calculator. Now, how many significant digits? Your wavelengths, your frequency is a measured unit. Your Planck's constant is a constant value. That doesn't count for significant figures. So we've got 3 significant figures here. So where do we draw the line for 3 significant figures? We draw it right there. And that rounds up to 50.3. Okay, now we do our exponents. We have 10 to the 34. And we have 10 to the 15. Okay, let me check all that here.
Wait, so it wasn't 10 to the 11?
Yeah, we're 10 to the, this is minus 34, hold on. Yeah. Planck's constant is 6.66 times 10 to the minus 34 joule seconds. And then 10 to the 14th, right? I said on there? Yeah.
Okay, there you go.
Yeah. Sorry, I the minus sign there. All right, so 10 to the minus 34. So what's 15, what's 15 minus 34? 10 to the minus 11, right? No, that's 6, that's not right. Ah,
19.
Yeah.
So there's nothing.
10, 15, 10 to the minus 19, right? 9 and 4, 34. Yep. So that becomes 10 to the minus 19. So you have 50.3 times 10 to the minus 3, 10 to the minus 19 joules. Okay. So let's put that in sign notation. It becomes 5.03 times 10 to the, we move the decimal point 1 place to make it smaller, make this bigger by 1 point, minus 18 joules. So come up with 5.03 times 10 to the minus 18 joules is the energy for light that has a frequency of 7.59 times 10 to the 14th.
Didn't we start off with 7.59 times 10 to the 14th though?
Right? Oh, did I put 15 here? Holy cow. This has not been my day. Man, that should have been 14.
Yeah.
All right, so this should have been 10 to the 14th here. So 14 minus 34 is 20, right? Negative 20. So this should be negative 20. Sorry about that. Okay, because you got minus 34 plus 14 is negative 20. Okay? And then we move this decimal point 1, made it 1 place smaller, make this one 1 place bigger. So minus 20 becomes minus 19. So it's 5.03 times 10 to the minus, times 10 to the minus 19. Okay, does that make sense now?
Yeah.
Boy. All right, perfect. So that's how you do with frequency. Now, what if you're given wavelength? So let's go to wavelength. And we're going to do this one. Hopefully nothing goes wrong with this one here. So say we have a wavelength. A photon of light has a wavelength of 653. I'm going to draw this neater. 653 nanometers. What's its energy? Okay, typical test question on your midterm. Okay, 653 nanometers. How much energy is that photon of light going to give off? Energy equals h times the frequency. We got to get that into wavelength. So we have 2 formulas here. We have energy equals h nu, and we have c equals lambda nu. So we rearrange this one here. Lambda, our mu equals c divided by lambda, right? So instead of writing mu here, I can write c divided by lambda. So energy is equal to h times c divided by lambda. So if you're given the frequency, you use this formula. If you're given the wavelength, you use this formula. And all I did to get it was substitute in this value here of mu, of the frequency. Okay. C, instead of writing frequency, I wrote C divided by lambda, which is what we have right here. Does that make sense? So far, so good? Someone give me a hands up, or can anybody hear me?
I can hear you.
Okay. Is that making sense?
Honestly, I'm not following too well because I haven't read chapter 4.
The underlined blue one is for what?
Okay, that's your frequency. Remember,
that frequency.
you have the formula C equals lambda mu. Wavelength times frequency equals the speed of light. So all I do is rearrange that. I put C divided by lambda equals mu. I just divided lambda to both sides. I can do that on just algebraic. I can do that inside the equation.
Oh, okay.
So instead of writing mu here, I can write C over lambda.
Oh, okay.
So then I got that formula. Okay. So now I got energy equals HC over lambda. I know H. H is 6.26, 6.626 times 10 to the negative 34 joule seconds. And the speed of light is 3.00 times 10 to the 8 meters per second. And lambda was 653 nanometers. Okay. I got seconds, that'll cancel, but I got nanometers and meters. So to get in the same units, you have nanometers on top and then meters on bottom. Nano is 10 to the minus 9. So now nanometers cancel, meters cancel, seconds cancel. I'm left with joules. Make sure you do your conversions right. Make sure you're canceling nanometers with nanometers and not with meters. So now we do all the math. We save. I'm going to save this for last. I'm going to save this for last. And I'm going to save this for last. Okay? So it's on the top you multiply, the bottom you divide. So, whoops, let me get my calculator back up here. Let's do 6.626 okay, times 3 divided by 635. And that comes out to 0.0313 0394. Now, what's my measurement? What's my measured value? I got 3 numbers there. Planck's constant is constant. The speed of light is constant. So those don't count as significant figures. Okay. My 635 is a measured value. That's my wavelength. So that has 3 significant figures. So my answer is going to have 3 significant figures. So where am I going to draw my line? Between what 2 numbers?
3 and 0.
3 and 0. There's 3 significant figures right there. So we're going to end up with 0.0313. And this number here is less than 5, so the number stays the same. And then I'm going to have 10 to the minus 34. I'm going to have 10 to the 8. And I bring this one up and change the sign, right? And 10 to the 9. So I have minus 34 plus 8 plus 9. And that comes out to 10 to the minus 17 joules, right? Minus 17 is 34, yeah. Okay, so far so good?
Yeah.
I move this decimal 2 places to make this 3.13. Again, make them between 1 and 10 times 10 to the And I made this number, I've made this number bigger, right? I went from 0.03 to 3. So I made it bigger by 2 places. I moved that one 2 times. So I'm going to make this number smaller by 2. So 10 to the minus 19 joules. That's a 9. All right. Finally did one that worked all the way through. And that's how you get energy. So now you can do, if I give you frequency, you give me wavelength. If I give you wavelength, you give me frequency. Okay? For energy, if I give you frequency, you give me the energy. If I give you the wavelength, you give me energy. I guarantee you'll see one of these on a midterm. You got to convert your wavelength, substitute frequency, and then convert that into joules. That makes sense? Those are the calculations with energy and frequency. That's it. That's what you need to know for wavelength and frequency. Okay? So there's 2 formulas. I mean, you don't have to memorize them. You just have to know how to use them. C, speed of light, equals your frequency times your wavelength. And energy equals Planck's constant times frequency. So with those 2 formulas, again, do not memorize them. And don't memorize the constants either. You'll have those. You can look those up. They'll be all on there. But with those 2 formulas, you should be able to calculate. If I give you frequency, you should be able to calculate wavelength. If I give you wavelength, you should be able to calculate frequency. You should be able to calculate energy if I give you the frequency, or energy if I give you the wavelength. With those 2 formulas, know how to use them. Know how to rearrange them to get what you want, and know how to use them. Okay? So that's frequency and wavelength. Any questions on that? And like you saw, it's very easy to make mistakes, especially with minus signs. Okay, because I do it too. The more you practice, the less mistakes you can make when it comes to the midterm. I'd rather you ask me questions and we do them again, and you get your mistakes out of the way. So kind of when you give questions for me, be prepared to work them with me, because that way you'll make the mistakes now when I can correct you, rather than making them on the midterm. All right, the second part of chapter 4, point 2, is the color that things give off. Every element, remember our periodic table? Every element, when you burn it, is giving off a specific color. And color is due to the electrons being excited and moving back down. So what you have is the Bohr model of the electron. Let's get a blank page here. So this is your proton in the center. Remember, protons have a positive charge in the center. And you got your energy rings. You got your rings going around your proton, your electrons spinning around your protons. Okay, this is n equals 1, n equals 2, 3, 4, where n is equal to your energy, what's called your energy level. Can't spell either. Okay, so there's different energy levels coming away from the center of the proton, of the nucleus. Okay? When you excite an electron, so there's electrons flying through here. There's different orbitals, and we'll get to how many electrons there is in each orbital. But when I take an electron and I add heat or add any kind of energy, I take an electron and I'm going to move it up into a different energy level. I can promote it. So energy can move an electron, because remember, there's a positive charge and a negative charge. They're being held together. So it takes energy to move them apart because they're being pulled together, right? Opposite charges attract. Now, once that energy is used and it's gone, what's going to happen to this electron that's out here? It's going to do what? It's going to fall back down to its original energy level. When it falls back down, it releases a photon of light. And each of these light is a different color, depending on which electron is promoted to the different energy level. That's how fireworks make all those different colors. They send up the different elements like sodium, phosphorus, potassium, whatever's in the firework, whatever color they want, sulfur. They send it up and then ignite it with a spark. That spark moves electrons to a different energy level. And we can control which one it moves to. Once the energy is gone, that electron slams back down and a different color is released. That's what makes all these different colors in your fireworks. That's exactly how they work. It's by these photons being released by the electron sliding back down after the energy is gone and going back to its original energy level. Okay, so those are what electrons do in your energy level. Every electron has a specific color. It's like a fingerprint. Okay? If you shine a light through sodium, it will give you, if you burn sodium, it'll give you a specific color. If you burn neon, it gives you a specific color. That's why neon lights glow a certain color. That's you control what color things are glowing by putting different elements in it and exciting them at different wavelengths for their energy. That's you get different color neon lights. Okay. Argon lights, sodium lights, and street lights nowadays give off a yellowish color. Okay. There's a specific band of colors given off, and it's like a fingerprint for each element. Every element is different. And this was called the Bohr model, B-O-H-R. Okay, so every color is different depending where it's going down from. Now we've got this, the quantum model of our electrons. These electrons are spinning around. Okay, we have different energy levels. Okay, so you get N is your energy level, and with periodic table, that's what your periodic table looks like basically. Okay, so we're going to assign letters to each one. Electrons are spinning around this nucleus, and we can't identify where they're at. We just know they exist, and they're moving around. We have a probability of finding them at a certain place. So we have different energy levels we assign to them. This column here, these two columns, these are your S's. Okay, this column here, the 6 columns are your P's. This column here, 10 columns are your D's, and this column here, if I'm color the green, are your F's. So S's have, your S's will have 2 columns, your P's will have 6, your D's will have 10, your S will have 14. So S, P, D, and F is how your energy levels are arranged. And we're going to use that to find out the address or the location of an electron. We have to tell what energy level that is located in. It's going to sound really weird at first, but if you just follow the periodic table, you'll get it right. Okay? So the rule to remember is where your S, P, D's, and F's are. And S's start with 1. P's start with 2. D's start with 3. And F's start with 4. That you need to know. So know where S, P, D, and F are in periodic table. Okay, no, S's are always going to start with 1. P's are always going to start with 2. D's are always going to start with 3. And F's are always going to start with 4. So there's no such thing as a 3F because F start with 4. There's no such thing as a 2D because D start with 3. Okay, and the rows going across your periodic table. Okay, these are your energy levels. So the first row energy, N equals 1. Second row, N equals 2. Third row, N equals 3, N equals 4, N equals 5. That's your energy levels. Okay, so remember the S's start with 1, the P is going to start with 2. Okay, so the energy level for P when it comes across here is going to be 2. And then 3, 4, etc., going down. D start with 3, so you're going to have 3, 4, 5 going down. And F start with 4, going down for your energy levels. Okay, so that's the basics of how we're going to do these sublevels. Okay. So we're going to describe how these electrons are located in the different energy levels that they can be in. Okay. So we're going to write different electron configurations. Basically, we're going to start with, start with hydrogen. Everybody pull up a periodic table. You see where hydrogen is, right? The electron configuration for hydrogen is what's called 1s1. So N equals 1. The first element, okay, hydrogen's right here. Okay. And there's 1 electron. Hydrogen is 1 electron. 1 proton, 1 electron. Remember how we did protons, neutrons, electrons? Okay. Then helium. Helium, for sake, just put it right here because helium is one of the S's. So we'll just slide helium over to here. Is 1s2. It's in the first column, energy level. it's in the S sublevel still, and there's 2 electrons. So helium is 1s2.
We can't see it.
Yeah, I was about to say that as well.
Okay.
When you started at hydrogen, it didn't show.
Yeah, we were, yeah.
Okay, that's why I was confused again. And let me try to pull up the chat window too, in case people want to write in chat. There we go. Okay, so hydrogen is 1s1, helium is 1s2. It's in the first row, first row, and there's 1 electron for helium, and there's 2 electrons for 1 electron for hydrogen, 2 for helium, and they're both 1s. Okay, then we drop down the next one. The next one going down is lithium. See where lithium is on your periodic table? Lithium's right here. Okay, that's, in fact, I should put in lithium. So lithium is right there. So we build on this. We go back to the beginning. So lithium, its electron configuration is going to be 1s2, because we filled that first column, and then 2s1. That should be 2. Okay. Become it n equals 1, 2, 3, 4, 5, 6 going down. That's all hydrogen on that. Okay, so all you're doing is following the periodic table. So kind of make this a little clearer. If we have our periodic table and we look at, let's look at boron. Okay, everybody see boron. Boron's number 5 on the periodic table, right? That looks like 15. Okay, can everybody see boron on the periodic table? Number 5.
Yes.
Okay.
Yes.
What you do is you're going to count electrons. You're going to start with hydrogen. Hydrogen, you see the numbers 1, 2, 3, 4, 5, 6 going down the periodic table to the left, all the way to the left side.
Yes.
Okay, those are your energy levels. So you always start with hydrogen. You have 1s1, and you go to helium, go across. That's 1s2. There's 2 hydrogens. So boron is 1s2. That gets you up to helium. Then we're going to drop down to lithium. Lithium's in the second row, and there's 2 s's there. There's 1 electron each one, so 2s2. Okay, there's 2 electrons, 1 in lithium, 1 in beryllium. And then you go to the boron. Boron's in the p column. Remember, p start with 2. S's always start with 1. P start with 2. D start with 3. F starts with 4. So 2p1. And that's your first one. That gives you the electron address of your electron configuration. If you add the superscripts, you will get this number. You'll get the number of electrons in it. So 2 plus 2 is 4, plus 1 is 1. So you have, and you're always going to start with 1s1, 1s2. You're always going to go back to hydrogen and start across your periodic table. And you use your periodic table to fill these in. Okay. If we looked at fluorine, let's do fluorine. Fluorine is what number? Fluorine's number 9.
9.
Okay. So we do fluorine. Fluorine starts with what? 1s2, because we filled in the s's. Then we drop down 2s2. We fill that in. We keep going right across the periodic table. Okay. And then we're on the 2 p's. And how many electrons are in the p's? We have 1, boron, carbon, nitrogen, oxygen, fluorine. So 1, 2, 3, 4, 5 electrons. So fluorine, the electron configuration is 1s2, 2s2, 2p5. Okay, is that kind of making sense? We're just filling it right across the periodic table. Kind of without seeing a periodic table. Okay, so let's go to neon. Neon is our noble gas. Okay. Neon has 10 electrons. So let's go back. Neon would be what? What would be the first one of numbers and letters?
You can't see your screen. Neon.
Okay, neon has 10 electrons. So what's the first numbers here? 1 S2, that's hydrogen and helium. 2 S2, again, just go across the rows of the periodic table. Go from 1, 2, 3, just along with the numbers. 2 S2, that fills your S's, that fills that column. Then you go to 2P6, because count your electrons from boron. 1 in the P levels. 1, 2, 3, 4, 5, 6. Okay, and that's a noble gas. This fills your valence electrons. It fills it up so it's stable. Whenever you fill that, that's stable. It gives you noble gas form. Okay, so let's try this. Let me try to draw another periodic table. I'm not real good at drawing. But here's your periodic table. And I slid helium over here. For this purposes, I just slid helium over here. Okay, so these are always going to end on something P6, whatever the energy level is. So these always start with 1. That's going to give you 1s1, 1s2. These always start with 2. These always start with 3. These always, and then down here, you've got your actinizing lithiumite series. These always start with 4. So that's how you do it. S's start with 1, the P's, so this is all your S's here. These are your S's, these are your P's, these are your D's, these are your F's. It always goes in that order. Okay? So whenever you count them at those levels, that's what you start with. All right, so let's pick let's do 10. Okay, if you can do 10, you can do anything. So 10 is SN and it's 50. All right. So someone tell me what we start with. Go back to hydrogen. What are you going to start with? S's start with 1. So 1, S, 2. Then you drop down to the next level because there's 2 electrons, 1 for hydrogen and there's 2 in helium. Helium has 2 electrons. Lithium has 3. So you drop down to 1s2, 2, and you're still in the S's, 2s2, and you fill that level. Then you go across to the P's. P's start with 2p6. There's 6 across there. Drop down the next level. What's the energy level? What's that number left of the periodic table? Three, right? 3s2, 3p6. Going across, there's 6 that fill across the third. Then you got down to the 4th level. You got 4s2. Now that's when we hit the D's, right? S, P, D's, and F. D start with what? What did I say D start with?
3.
3. So 3, D, and there's 10 going across the D's. Okay, and then we're back at the P's after that. And we're at 4, because remember, P start with 2. So we're at 2, 3, we're at 4P. And we're at 6, we go across. We go down to 5. 5S2. So 4D10, 5P2. So that's electron configuration for tin. If you can do that, you can do anything, any of them, because you can stop along the way. Okay. So use that as an example to write any of them out. And then we'll do one more thing where there's you don't have to write it all like that. There's what's called a noble gas abbreviation, which means you can go back to the nearest noble gas and then write the remainder. So you don't have to write the whole thing out. In other words, okay, so there's tin. So know how to do that. You can stop at any place on it, any other one. Let's do phosphorus. See where phosphorus is? Number 15. Go backwards, 14, 13, 12, 11, 10. That's the nearest noble gas. So you can write noble gas in brackets. That means there's your electron configuration for neon. And then you write the rest. So neon, then you go to sodium, which is 3s2 for phosphorus, and 3p. And phosphorus is how many? It counts on 13, 14, 15. There's 3. So that's the other way to write phosphorus. That's called the neon gas abbreviation. So you get real big ones like copper and stuff like that. You don't have to write all those out. Just go back to the nearest noble gas. So know how to write it both ways. You'll have to write on your exam, on your midterm. All right. I lost my chat window again. It loses chat every time I do that too. Okay, so if you put something in chat, just yell at me if I can look at it. All right, so let's do calcium in the noble gas form. Everybody see calcium. Calcium is number 20 on the periodic table. So back it up. What's the nearest noble gas for calcium going backwards? Just count backwards. 20, 19, 18 is the nearest noble gas, right? Noble gas is your right-hand side. So that's argon. So put argon. And what's the energy level for calcium? You have 1, 2, 3. It's in row 4 for the S's, right? So 4. And calcium is S. And there's 2 in the S's. That's what fills your orbitals in. Okay. So this is the electron configuration. This top one up here. Okay. This is the noble gas core abbreviation for the electron configuration. Know how to write it both ways. Okay? And all you're doing is counting across the periodic table. You're going straight across. You're filling one row at a time. Once one row is filled, you drop down to the next one. Then drop down to the next one. Then drop down to the next one. And just count your electrons. Know where your S's are. Know where your P's are. Know where your D's are in the center and your F's on the bottom. And know that S's, you're always going to start with 1. The P's, you're always going to start with 2. The D's, you're always going to start with 3. And the F's, you're always going to start with 4. Okay, so those are your configurations. I think that is what they have for this chapter. Because we're going to use this information as what's called your outer electrons or your valence electrons. Those are the electrons that react. So in other words, if you look at what I wrote with calcium, there's a core of argon and there's 2 electrons outside of it. These 2 electrons, these are what's called valence electrons. So calcium has 2 valence electrons. 2 valence electrons. Okay. How many valence electrons does phosphorus have? You have your core. So how many electrons do you have extra? Somebody give me a number, a guess.
Assuming 3.
3 plus?
2, so 5.
5, perfect. They're outside the core. You have 3 and 2. So phosphorus has 5 valence electrons. And everything under phosphorus is the same way. So every group, every family, every column is going to have the same number of valence electrons. So I'll look at oxygen. Let's go to oxygen. Oxygen is, if you go backwards, helium is your nearest noble gas. And then you've got 2s2, 2p4. So how many valence electrons does oxygen have?
6.
6. Perfect. It's exactly what we're going to be using. Okay. So oxygen, sulfur, selenium, tellurium, every one of those in that column has 6 valence electrons. Okay. Let's look at sodium. Sodium is Na. And it has 11 electrons. It has neon going backwards, and then, oh, where am I at? 3s1. So sodium has 1 valence electron. So hydrogen, lithium, sodium, potassium, rubidium, cesium, francium, all of those have 1 valence electron. That's why they're so reactive. They want to get, everything wants to react to become stable, to become this noble gas core. That's why these are important. Okay? So sodium is going to lose 1 electron to become stable. So it's going to be, sodium is always going to form Na+. It's going to lose 1 electron, giving you 1 extra positive charge. Beryllium, magnesium, calcium. Okay, those are always going to lose 2 electrons. Okay, because those have 2 valence electrons, and they're going to be Ca2+. Boron and aluminum, they're going to lose 3 electrons. Aluminum is going to be 3+. Okay, because they have 3 extra electrons on aluminum and boron, gallium, indium. Calcium, magnesium, beryllium, strontium, those always have 2 extra electrons. So you're going to lose those. So they're going to have positive charges. So sodium, that whole column is going to be +1. That next column is going to be +2. And the one all the way over to the beginning of the right-hand group of P's is always going to be +3. Now, when you get to the carbon column, carbon is neutral. Carbon has how many valence electrons? If we write the core for carbon, go back to the nearest noble gas for carbon, which is helium. And then carbon has 3s, where am I at carbon? I'm sorry, 2s2 and 2p2. So how many outer or valence electrons does carbon have?
4.
Carbon has 4. Okay. Now all the noble gases have 8 in that last column. It's always going to be, they're always going to have 8 valence electrons, which is stable. So 4 is right in the middle. So if it has less than 4, it's going to give up an electron. If it's got more than 4, it's going to bring electrons into itself. So less than 4, the first column, the second column, and then the 3A, boron aluminum, those are all going to lose electrons. The first column is going to lose 2, the second is going to lose 1, second column is going to lose 2, and then the boron, aluminum, gallium are going to lose 3. So you get +1, +2, +3. Then you hit carbon. Carbon doesn't lose any or gain any. Carbon's right in the middle. It forms what we're going to go over later. It's called covalent bonds. That's why carbon is the basis for organic chemistry, because it doesn't have the ion to form. It's our neutral one. That's why it's a basic element for organic chemistry. Okay, so let's continue past carbon. So let's go to nitrogen now. Let's go to another screen, and I lost my screen again. Dang it. I've never had this happen. I don't know what is going on with this thing. It's never kicked on my microphone before either. Something's going on. All right, so then we go to nitrogen. Nitrogen is helium, 2s2, 2p what? 3, right? So how many valence electrons or outer electrons does carbon have? And that's nitrogen.
5.
Nitrogen has 5, right? Which is more than 4, so it's great. So it's gonna bring in 3 electrons. It's gonna add 3. So nitrogen is gonna have a 3- charge. because it wants to bring in 3 more negative charges to what it has to make 8. Everything wants to make 8. It'll either lose 1, 2, or 3 to go backwards and make 8, or it'll gain 1, 2, or 3 to make 8. And if it's in the carbon column, it's going to stay neutral. So nitrogen, phosphorus, arsenic, antimony, all those are going to gain 3 electrons. So they're going to be 3 negative. Okay. Oxygen. We did oxygen. Oxygen is helium. 2s2, 2p4. So how many valence electrons does oxygen have?
6.
6, right? So it wants to bring in how many electrons to make it have 8?
2.
2. So oxygen is going to be 2 minus. Oxygen, sulfur, selenium, whenever we use those in a formula, they're going to have a negative 2 charge because they want to bring in 2 electrons to make them stable. Okay? So all those columns are negative 2. Fluorine, chlorine. Fluorine is, these are the halogens. There's helium, 2s2, 2p5. That's 7 valence electrons. They want to add 1. So fluorine, chlorine, they're going to be negative 1. Okay, that's how we determine all these charges. That's it. By these electron configurations and our valence electrons. So overall, looking at the periodic table, the first column going down is going to be +1. The second column going down is going to be +2. The ones in the middle are transitional. They can be different positive charges because their electrons share different levels. When we get to the 3A column, boron, that's going to be +3. Carbon is neutral. Nitrogen group column is -3. Oxygen is -2. Fluorine column is -1. And then the noble gas is 0. So if you write on your periodic table, write +1, +2, skip the transitional metals, +3, 0, -3, -2, -1, and then 0 again. And that's how we determine the charge on our elements. Okay? So it just, everything wants to be stable. Okay? So if we're going to write the electron configurations, okay, they're going to want to be like a noble gas. Okay? So if I took oxygens, for example, let's hit oxygen. If oxygen is going to be -2, we're going to add 2 electrons to that. So it's going to have the same electron configuration as neon. It's not going to be neon, but it's have the same number of electrons as neon. Okay? It's still going to be oxygen, but it's going to add 2 electrons. That gives it a total of 8, and that will give it the same configuration as neon. These are called isoelectronic series. Isoelectronic series. Okay, those are series that have the same, all the elements in it have the same number of electrons. Okay, they're not the same element, they're all different elements. So an isoelectronic series would be like O2 minus, F minus, okay, neon, Na plus, Mg2 plus.
I think it stopped writing again.
Darn it, thanks. Dang. It's getting long and long before, so isoelectronic series, same number of electrons. So O2 minus oxygen, look at the periodic table. How many electrons does oxygen have? Just look at your periodic table. Remember, protons and electrons are equal if there's no charge. So what's the atomic number of oxygen? What's the big number that oxygen is on the periodic table?
8.
8. Okay. And I've got 2 minus, so 2 extra electrons. So 8 plus 2 is 10. How many electrons does fluorine have?
9.
9.
9, perfect. And we have 1 extra one, right? This negative charge right here. We have 1 extra electron. So we have 9 You have 10. Neon. What's the number for neon?
10.
10. Sodium. What's sodium?
11.
11. It's a plus 1, so it's minus 1 electron. So 11 minus 1 is 10. Magnesium is what? 12. And it's a plus 2. Okay, so that's 10. They all have 10 electrons. So on your midterm, I'm going to give you a series of elements. And you have to tell me which one of these series is an isoelectronic series. Isoelectronic means same number of electrons. I mean, O2 minus is not neon. O2 minus is not Mg2 plus. It's still their own element, but it's the same number of electrons, so it's stable. Okay? If you're not changing your element, you're not changing the number of protons, because the number of protons determine your element. You're not changing the number of protons. You're strictly changing the number of electrons. You're either adding electrons, which makes it more negative, or you're taking away electrons, which makes it more positive.
So it's parentheses 34.123 plus 5.60 over 98.7654 minus 8.492.
8.492.
Correct.
All right. So do 34, do the top first. 34.123. 34.123 plus 5.60. Okay. That comes out to 39.723. And you're only good to the least accurate number. It's only good to 2 places past the decimal. So this comes off to 39.72. That's your top number, right?
Yeah.
You're only good to 2 places past the decimal, okay? And then the second number on the bottom is 98.7654. 98.7654 minus 8.492. 8.492. 8.492. That comes out to 90.2734. And you're only good till 3 places past the decimal on this one. It's only good to right there. So you're only good to 90.273. Okay? So far, so good?
Yeah, how come for the 39.723, you're only good for 2 places, and then for the 90.293, you're good for 3 places?
Yep. Those are the least accurate for each one of those. And then you divide 39.72.
Yeah, but I was asking how come it's different. Like for the first one, it's 2 places, and then for the second one, it's 3 places.
Because your least accurate number right here is 2 places. Your least accurate number right here is 3 places. When you add and subtract, it's the least accurate number.
Okay, my bad. I understand now, because the 39.72 was from the top number, so it goes by the 560, and then for the bottom figure, it goes by the 8.492, correct?
Least accurate number, yep.
Okay.
So far, so good?
Yeah.
The 39.72 divided by 90.273 comes out to 0.43999.439999867. We're good to 4 significant digits. That's our least number we're multiplying or dividing. 1, 2, 3. We're only good to right there. Right? So 4399 rounds up to 0.4. Where are we at? We're going to round this one because this is greater than 5. So that rounds that up to 0.44. We're good to 4 significant digits, 0, 0. Right? So that rounds that up to 144. So this would be your answer. That rounds up to 4 significant digits. So 0.4400 would be what that rounds off to. And that's 4 significant digits, which is the number right here. This has 4, this has 5 down here. So you're only good to 4 significant digits. So it's good right to here. And this rounds up. So it rounds all this up, rounds this up to 4. So it rounds up to 0.4400.
Okay, so it doesn't go by the significant digits out of the whole problem, the whole original problem. It goes by the 2 outcomes
Sure it doesn't.
from.
When you're adding and subtracting, the different rules of multiplying and dividing. So you got to do those separate.
Okay.
Yep. If it was all multiplying and
Okay.
dividing, the whole thing, then do it. But if you got adding and subtracting, you got different rules of multiplying and dividing. Because adding and subtracting is the least accurate number. Multiplying and dividing is the least number of significant figures. So 2 different things. Make sense?
So you said, yeah, so it was 0.4400.
That's the answer. Yep. That would be the 4 significant digits.
So for adding and subtracting, you said it's for the significant figures. What's the rule again?
No, adding and subtracting is the least accurate number.
Okay.
Multiplying and dividing is the least number of significant figures.
Okay, got it.
Okay, perfect. Other questions?
I have a question back to chapter 4.
Okay.
I just opened it up, but
Okay.
so they give you, like at the beginning when you were talking about wavelength and frequency.
Right.
So the wavelength would be like the nanometers in between like the lines that you're making, correct? So the longest wavelength would have the longest gap in between this, like the squiggly line. I wish I could like draw it and show you what I'm talking about.
That's the wavelength. I just drew that. That's your wavelength.
Okay, yeah, so that's the wavelength. So then the greatest frequency one would be the one with less wavelength in between, correct?
Right, that'd be a greater frequency. Frequency is if you draw a line right here, where this point is, where this point is, where this point is, the same point, how many times it passes that line in 1 second.
Oh, okay. And then the greatest energy would be, that's the one I was a little confused on, the greatest energy.
Think of it this way. Think of it, if you have a wavelength that looks like this, or if you've got a wavelength that looks like this, which one is more energy?
The crazy one?
Yeah, the one that goes really fast.
Oh, okay. So that would be greatest. Okay. Just wanted to clarify so I understood it properly.
No, that's perfect.
Just because I was looking at chapter 4.
Yep, no problem.
I think we're opposite people because I understood that one right away. I don't understand the configurations and you understand it.
So it comes to you. Just practice, it'll come to you. Because it's just counting. Once you figure out you're just counting, it clicks. So how does, oh, I had a question on the last one too. How does 5.6 being added? Because when you add this, you're only accurate for, this is for Tara's put it on chat. You're only accurate to 2 places past the decimal, the least accurate number. So then your answer can only go 2 places past the decimal. So it's 39.72. When you're adding and subtracting, but you do that first, then you're only accurate to your least accurate number. So you can only go 2 places past the decimal. Doesn't matter how many significant figures it is. Okay, good, perfect. You got to remember the different rules. Adding, subtracting is the least accurate number. Multiplying, dividing is the least number of significant figures. Perfect. Other questions? Everybody questioning out?
I have another one.
Okay, go ahead. And I'll have a periodic table. We'll be able to go over that electric configuration again on Wednesday too. I'll make sure.
Yeah. Thank you.
No problem. What's your question?
Okay, so this one says convert 4.09 times 10 to the negative third power meters to the equivalent length in nanometers.
Okay, perfect. We're doing conversions. Write down what you're starting with. 4.09 times 10 to the negative 3 meters. Draw your line. And then you put meters on the bottom so they cancel. And you want to go to nanometers. Then you make this block equal to 1. So nano means in metric system 10 to the minus 9. That's the exact same thing as writing n. So instead of writing n, I can write 10 to the minus 9. That way this becomes 1. So you're not changing the number value, you're just converting it to different units. Okay, so nano's 10 to the minus 9, so meters cancel. And this becomes 4.09 times 10 to the, remember you bring this up, you change the sign. So minus 3 plus 9 becomes 10 to the 6 nanometers. Okay. So you just, whenever you do exponents, you bring it up, it changes the sign, then you add them. When you multiply exponents, you just add.
Can you say the last part again? I'm sorry, it got cut off.
Oh, no
My
problem. When you're multiplying exponents, you add them together. You just move the exponent up to the top line and change the sign, and then add them together. That's how you multiply exponents.
Okay.
Professor, I'm questioned out. I think I'm gonna hang up.
Okay.
Thank you so much for today's lesson.
You're welcome, Taylor. No problem.
Thank you. I'll see you Wednesday.
That sounds good.
All right. Thank you. Bye, guys.
Bye-bye. All right. Any other questions, Cassandra?
Yeah, I'm looking. Oh yeah, okay, here we go. While driving a rental car on your vacation in Europe, you find that you're getting 10.7 kilometers per liter of gasoline. What does this value correspond to in miles per gallon?
Okay. So 10.7 kilometers. And I want to change that into miles. So kilometers. Kilo is 1,000, so 10 to the third miles. 10 to the third meters. And I know there's a conversion there, but I would do 3.2, I can convert meters to feet. There's 3.28 feet per meter. And there's 5,280 feet in a mile. That gives you miles. And then you convert, so you got kilometers to meters, meters to feet, feet to miles. That's one way to do it. And now I gotta get liters into gallons. I don't know the conversion. I have to look on a conversion chart for that. Convert, so you'd have kilometers per liter. Sorry about that. So how many liters per gallon? I have to look that up. I don't know the top of my head. I don't want to do this and lose this again. Let's do it this way. Let me do it on my cell phone. Let's go to liters to gallons. Water. Liters to gallons. All right, so liquid gallon, what's that? 1 liter is 0.26. So 1 liter is the same as 0.2642. 0.2642 gallons. So there's 0.2642 gallons per liter. You got kilometers, meters, feet, left with miles, and then liters cancel, left with gallons. So take 10.7 times 10 to the, well, times 3.28 divided by 5,200 feet divided by 0.2642. Does that make sense?
Yeah, I'm putting it in my calculator right now.
Oh, okay. And then times 10 to the third at the end. So I have 10.7 times 3.28 divided by 5,280 divided by 0.2642 equals that, and then times 10 to the third. I get roughly around 25 point some, if I get the numbers right.
How would you times 10 to the third on a regular calculator?
Times 1,000. Move the decimal point 3 places. So in other words, you come up with 0.0252. Just move it. If you times 1,000 is 1, 2, 3. So 25.2 miles per gallon. Okay. All exponents mean is move the decimal. If it's 10 to the 3, move the decimal point 3 places. Make the number bigger because it's positive. If it's 10 to the negative 3, move 3 places and negative. It just tells you how many places you can move the decimal point, and positive, negative, which direction. If it's positive, you go to the right to make it bigger because you multiply by 1,000. If it's negative, you move to the left that many places. That's all an exponent is. This tells you how many places
Oh, okay.
you move the decimal.